Let us get started for today. The topic at the beginning today will be the so-called Banach Spaces. So they are named after a famous Polish mathematician that lived for about 80 years ago. Before we start with the Banach Spaces, let me just remind you what we did last week. So we looked at the so-called normed vector spaces. So let me just start by reminding you about these spaces. So we had the definition last week. So the way to define a normed vector space was to say, let's take any vector space, and then assume that we have a function which we call, these double bars on each side. So this should be a mapping that to each element in the space associate a real number. And the conditions to this mapping is that it should take values that are greater than or equal to 0. It should be 0 if and only if the element is 0. If you look at the value of alpha times a vector v, this should be the same as just the absolute value of alpha times the norm of the v. And then there's the triangle inequality saying that if you look at what we call the norm of v plus w, this is smaller than the norm of v plus the norm of w. And we saw already a very important space, a very important example of a normed vector space, namely what we call the continuous functions on the interval a to b. So this is just a set of functions defined on the interval a, b, taking complex values. It could, of course, also just be real values, but they might be complex, and with the assumption that the function is continuous. And then we saw that we could actually define a norm of that space simply by taking the maximum value of the absolute value of the function values. And since this norm will be used again and again, we decided to put a special name for it, so we defined it with a norm symbol and then with this little infinity symbol below. So already again today, you will see that we will actually work with that space. Now, this was the normed vector spaces. We had one more concept last week that I would like to remind you about. Because we also introduced the concept of convergence in normed vector spaces. And you just saw one example, and you did a little bit at your homework about that, but we did not really go into details about that. But we'll do a little bit more about that today. So we say that a sequence in a normed vector space so let me just formulate it in short. So I'll not write in a normed vector space, this is understood. So I just say in V, it converts to some element V in the space if you just write it in a short way, the condition is that if you look at the norm of the difference V minus Vk, this should go to 0 as k tends to infinity. And I wrote down for you what it means in terms of epsilons. So let me just repeat that, because now we need the exact definition. So the exact definition is, whenever you take any epsilon that is greater than 0, you should be able to find a natural number n, such that this expression that we want to tend to 0, this is at least smaller than or equal to this given epsilon, as soon as the index k we are looking at is larger than or equal to the value k. So this is the way we define convergence. And none of you complained, maybe because you're used to people writing strange definitions on the board. But actually, if one of you complained, I would have somehow been happy about that. Because the definition is correct, but you can see there's a problem with the definition. You are looking at just the sequence Vk, and you want to define that this is convergent. But you cannot check this definition just by looking at the Vk. In other words, in order to use this definition, you have to have a good guess of this element V that the sequence should converge to. If you cannot guess what this V should be, then there's no way that you can use the definition, because the definition uses the difference between v and vk. So there's a problem with this definition. Mathematically it is correct, but it is not so easy to apply. So the problem is we need to be able to guess the v in order to use the definition. And you know, sometimes when we are speaking about convergence, we are just speaking about something that has to do with numbers, or we are speaking about something that has to do with functions. And in these cases, it might be possible for you just to guess the v. But in many other cases where you're just working with abstract normal spaces, it is very difficult for you to guess what the element v should be. And therefore we need to do something about this. And what we will do is to introduce a new definition that turns out to give a solution to this problem. So what we define now is not the same concept, but this is something that will help us to solve the problem we have here. So what we'll define here is the concept of Cauchy sequences. So we say that a sequence, and we denote it by the same as before, so this is still something vk, k from 1 to infinity, and this is still a sequence of elements in V, and this is a Cauchy sequence if, and now we put the condition that should replace the one we have here. And the way it will be formulated is very similar to what we have here, but there's a small difference. So again, we say for all epsilon greater than 0, there should exist a number n in the natural numbers such that, and then instead of doing what we are doing here, where we compare the v and vk, we'll just compare two elements in the sequence. That means we will require that if you look at the norm of vk minus another element in the sequence, some elements vl, this should be smaller than or equal to epsilon for all k and l that are larger than n. So you see, instead of doing what we do here, where we say we want to have a limit element v, and we want to get closer and closer to the v, what we are doing here is to say that we just look at all these elements in the sequence, and then whenever the indices k and l are getting large, we want the distance between the elements to be smaller and smaller. So this measures the distance between some elements in the sequence. There's an exercise today. So this is something you can show. And this is actually a lemma in the book. Or an exercise today. So you can prove that if you have a sequence that satisfies the condition we have here, that means if you have a sequence that is convergent, then it also satisfies this. So this is a very important exercise, in particular for those of you who did not have Mathematics 3, because this is maybe for you the first time where you have to compare something that is defined in terms of epsilon and n, and how to make two definitions of this type work. So please don't hesitate to ask me or ask your instructors when you come to the problem session. So you see, somehow this is a good news we have here. Every convergent sequence is a Cauchy sequence. But the question is this really what we want? So if I ask you, do you feel that this lemma solves our problems? Bjørn?
That depends on whether the sequence actually is convergent, because that isn't necessarily true in any space.
So you say it depends on whether the sequence is convergent. In a certain sense, that's clear because it says if you have a convergent sequence, then it is a Cauchy sequence. So I understand what you mean, but what about the problem? What can we say about this? Do we have a solution to that? What is your name? Jacob. Jacob, yes.
Well, we would like to know whether a Cauchy sequence is convergent, so we would need the other way.
So you say we would need exactly the other thing, and that's absolutely true, because what we're doing here is to say every convergent sequence is a Cauchy sequence. That means every sequence that satisfies the complicated condition will also satisfy the new definition. This is not what we want. We want exactly the opposite, as you say. And the good news here is that in many Banach spaces, the opposite actually holds. Not always, but in many spaces, the opposite holds. So now I will just define these spaces, and these are exactly the ones that are called Banach spaces. And then after that, we will look at examples of these spaces. So we formulate them in terms of a definition. So you can say, in a certain sense, this definition is cheating, because we have a problem, and this definition is just formulated by saying, now we will look at the spaces that have exactly the property we want. So what I will do here is to say a Banach space, this is simply a space for which all Cauchy sequences are convergent. So we did not prove anything, we just state that this is the class of spaces we want to look at. So a Banach space this is a normed vector space that has the property that all Cauchy sequences are convergent. So I would like to formulate that in a very detailed way. So I'll say, so in which each Cauchy sequence k from 1 to infinity converges to some element in V. So, the solution to our problem and you might say it is not really a solution, it is more in terms of now we have put down a definition for what we want. So the solution is that we will restrict our attention to Banach spaces. Because in Banach spaces, then you can just check our definition 3.1.1 instead of the real definitions of convergence. So you might say, this is not really a solution, this is just that now I tell you what we want to do. But the real good news today this is that all the spaces we will look at in Mathematics 4, they are Banach spaces. And it is not just because in Mathematics 4 we choose to look at these easy spaces. This is because when you go out in the world as engineers, most of the spaces you will meet, they actually have this property. So it's not that we just look at something because it's mathematically nice, but it's also because this is a real big class of vector spaces, and they cover most of the spaces you will meet in real life. So the good news is that all spaces in Mat4 plus most spaces in engineering they actually have this property, so they are Banach spaces. So of course this is something that is easy for me just to claim that the spaces are like that, but let's look at some examples of such spaces. So first, actually the spaces you knew since high school, the real numbers, and since Mathematics 1, the complex numbers, Rn, Cn, all of these spaces are actually Banach spaces. So if you look at Rn, or let's just write R, you look at C, or you look at Rn, Cn, then they are Banach spaces. And actually, if you look at in the book, you will see proofs of these statements. I do not plan to do that because then there will be too much overlap between this course and Mathematics 3. So some of you have seen this in Mathematics 3, so I will not discuss that. But I would like just to take this for granted. Now we say, okay, this is accepted. We will use that without any proof. And then we will use that to consider exactly the vector space that we introduced here, the vector space of continuous functions on the interval AB. And then we will prove that that space is a Banach space. So the vector space consisting of continuous functions on the interval a, b is a Banach space. You see, every time you use the word Banach space, then it means that you're already working with a norm vector space. So in principle, you would need to say, this is a Banach space with respect to a certain norm. You always need to tell what norm are you speaking about. I don't do that here because this is somehow understood that every time we work with the space of continuous functions AB, then we keep it with the supremum norm, the maximum of the absolute values of the functions values over this interval AB. So we always take the same norm, unless that I tell you something else. So if there's no text, it will always be that norm that we are using. So let's prove that. So in order to give the proof for that, you need to look exactly at what the definition says. So the definition says a Banach space is a norm vector space in which each Cauchy sequence actually converts to some element in the space. So that means the definition tells us how we shall prove this statement. We need to start with a Cauchy sequence, and then we need to show that it converts to some element in the space. So we take a Cauchy sequence in the space. That means now, because it's a space of functions, we don't use the vk anymore. So let's call it fk instead. So this should be a Cauchy sequence in C, A, B. And let's write down right away what this means. So now we can actually just refer exactly to the definition that we have up here. So this means for all epsilon that are given, there exists a number n such that if we look at two elements, fk and fl, and then fk minus fl with respect to the norm, then this will be smaller than or equal to epsilon for all k and l that are greater than n. And what do we need to show? We need to show that this converts to some element in the space. So we must show there exist some functions which we could just call f, and it should be a function sitting in the space, because this is what it says here. The sequence should converge to some element in the space. So this means the function f which exists should be a function that belongs to the space C, A, B, such that the norm of f minus, and then usually I would write norm of f minus fk goes to infinity, f minus fk goes to 0 when k goes to infinity. Actually, it turns out when we're doing the proof, you see there is a k and there's an l, and the way it comes out in the proof is that we actually show that f minus fl goes to 0 for l going to infinity. But this is just a matter of changing the letter k to a letter l. So, you see, this is not so easy to prove this statement, because how can we get hold on this function f? How can we find this function f that the sequence should converge to? And the idea is to use the relationship between the function values for the function f and this infinity norm that we have here. So, whenever we take any x, and then we consider fk of x minus fl of x in absolute value, then we know something about the size of this complex number that comes out here, because this will always be smaller than or equal to the maximum value for all these functions values that are coming out here. So if you look at a particular value of this function, this is smaller than the maximum value over all x. So this is smaller than or equal to max over all x in a, b of exactly the same thing. And if you look at what we have here, this is exactly our definition of our norm. This is what you see here on our slide, that this is exactly the way we have defined the norm on our space. So that means what we have here, this is exactly the norm of fk minus fl infinity. So what we get out of this is, I don't know if I'm supposed to point with this, but I think I can use it. So what we get out of it is, we know something about this difference. We know for all epsilon greater than 0, there exists an n such that this difference is smaller than epsilon for all k and l greater than n. But this one is greater than what we have here. This means that the statement we have here can be revised. So we can also state that for all epsilon greater than 0, there exists an n. We know there exists an n such that all this is smaller than epsilon. But if this is smaller than epsilon, then certainly this is smaller than epsilon, because this is smaller than the norm we are looking at. So we can state that fk of x minus fl of x in absolute value, this is smaller than or equal to epsilon for all k and l greater than or equal to n. And now we need some more space on the blackboards. So while I clean some of the boards here, I would like to ask you to think about this statement here. What does it tell us? How can we use this? So we need an interpretation of that statement. So do anybody have any comment about that? What does this statement mean? Rune?
Means that for a particular choice of x, the two different functions of x is less than epsilon.
Yes. So you say that for this choice of epsilon, this distance is smaller than epsilon.
Yeah, for a particular choice of x.
Whenever you fix any x, then this distance is smaller than epsilon. This is true. And what does this mean in terms of Cauchy sequences? Jakob?
Well, for a fixed x, the function value is a Cauchy sequence in real numbers.
Exactly. Well, this statement says that now we got a new Cauchy sequence. We started with a Cauchy sequence consisting of elements in the vector space. Here we are speaking about functions. We are not speaking about function values. We are speaking about this function and this function. So this is a Cauchy sequence in the vector space. Now we have fixed an x and we have put in the x here. So this is just a complex number. This is the function value of the kth function in this chosen x. We have fixed the x minus the function value of the function fl in x. So what we see here is exactly that the sequence of these complex numbers, they form a Cauchy sequence. So now I'll write it down in many words. This shows that the sequence of complex numbers namely exactly the sequence where the kth element is fk of x this sequence is a Cauchy sequence. And then a Cauchy sequence in C. So if you just went out of this room and you had to come back and then you should write down the definition of what does it mean that fk of x is a Cauchy sequence, and then you open your book or you look at the blackboard and see the definition, then this is exactly what you would write down. So now we have moved from having a Cauchy sequence in this vector space to have a Cauchy sequence in the complex numbers. How can we use a Cauchy sequence in the complex numbers?
We know that C is a Banach space.
We know that C is a Banach space. This is what we wanted to state up here. So this is a Banach space. So this means that all Cauchy sequences in this space are convergent. This means that this sequence is convergent. So I'm sorry for that I have to move here. So since C is a Banach space, our Cauchy sequence fk of x, k equal to 1 to infinity, is convergent. That means we can write down some limit. And since we are looking for a function that our sequence converges to, it is very natural to guess that this limit for the sequence we're looking at, this should be exactly the one we're looking for. So what we'll do is to write down the limit of fk of x for k going to infinity. Now we know this exists. We just need to find a name for it, and the natural name would be to say this is f of x. So that means now we actually have a function in our hands. And then what we can check is that this function is actually the one our Cauchy sequence converts to. This just gives us a guess for a function. This function f is defined by saying whenever we fix an x, then the sequence fk of x will converge to f of x. What we need to show now is that the sequence of functions fk also converges to f in the sense of the norm we have in our space. So what we need to show here that whenever we look at the difference between f and, again, you would think that I would write k, but in the proof it actually comes out as an L. So whenever we look at this difference, then it goes to 0 as L goes to infinity. And actually we need to prove one more thing. We need to prove that this function belongs to our space. So we need to prove that f is also a continuous function. So let's see how we can do that. If you go back and we look at this one, then it says that whenever we take any epsilon greater than 0, there exists an n such that fk of x minus fl of x is smaller than or equal to epsilon for all k and l greater than n. Now, I get the idea that I will let k go to infinity. So if you look at this, and we let k go to infinity, what do you get out of this? You get, when you let k go to infinity, fk of x converts to the f. That means you get that for all epsilon greater than 0, there exists an n such that, and then here you just have f of x minus fl of x. This is smaller than epsilon for, and then for l greater than n. This is what you get out of it. So what comes out is, for all epsilon greater than 0, there exists an n in the natural numbers, such that fk of x, but now we let k tend to infinity, and then the fk of x converts to f of x. So that means we just get f of x minus fl of x. This is smaller than or epsilon, smaller than or equal to epsilon for all L greater than n. So what this actually shows, this holds no matter how you choose your x. No matter how you choose your x, you get the same value for your n. So what this proves is that if you simply take the maximum value of this over all your x, then what comes out is that f minus fl measured in the infinity norm. So let me again just write it down. So the max over x in a, b, f of x minus fl of x. Since all of them are smaller than or equal to epsilon, then also the max of them will be smaller than epsilon. So this is smaller than or equal to epsilon. So what this says, for all epsilon greater than 0, there exists an n such that this infinity norm is smaller than epsilon whenever the L is larger than n. So what this shows that this norm actually tends to 0. Now, this proves one of the two things we had to prove. This proves this one. We also had to prove that f belongs to CAB. So I will actually not do that. I'll just state the reference to the book. So this turns out that this follows from a certain theorem. And actually, there will be a proof of this theorem at the next problem session, so the problem session in the next week, but it will be put as one of these extra exercises. You know, sometimes I have this text that I'm confident that the program is long enough, but if some of you want extra challenges and so on. So this proof will be put as one of these exercises. So those of you who really want to go into details with the mathematics, you will see the proof of this one. So this actually completes the proof. Now we have showed that given this arbitrary Cauchy sequence, then we have defined a function f such that the Cauchy sequence actually converts to this function f. Now I can also feel on you that some of you are losing the patience when you see arguments like this. This is actually very technical, and I actually don't plan to let you prove that any space is a Banach space, because it is technically a little bit too complicated. Now you have seen how it can be done, but this is not something that will appear in the exercises. So what I will ask you to do many times is to show that some spaces are normal vector spaces, but I will not ask you to prove that a space is a Banach space. Nevertheless, it's an important concept, and now we have seen our first example of a Banach space. I mean, we have seen a couple of examples. We have seen the real numbers, the complex numbers, and even to the power n, but now we have seen the first real interesting space that is a Banach space, namely the continuous function on the interval AB. What I would like to do before the break is to introduce another Banach space for you. So let's do that. So let's again start by something that you know. We look again at the fourth space up here, c to the power n. So let's speak a little bit about the space Cn. So the space Cn, what is that? That's the collection of all finite sequences with n coordinates. So this is collection of sequences. So if you write it short, this means that we are looking at a certain x in the space, but this x can be written as x1, x2, and so on up to some xn. And the special feature of this sequence is that all of the entries, x1, x2, up to xn, they are just complex numbers. So xk belongs to the complex numbers for k equal to 1, 2, up to n. What we will do now is to introduce a completely similar space, but instead of just taking n coordinates, we actually look at a sequence with infinitely many coordinates. So we will consider what I will call infinite sequences. So that means we will use exactly the same notation. We'll write x. This is then x1, x2, x3, but then it continues like this. And this is then again where xk belongs to c, and now this should be for k. It should not just be 1, 2, up to n, but it should be for all integers. That means for k in the natural numbers. We will define a special subset of the sequences of this type. And maybe you remember this strange notation I had last week. You know, I defined some spaces of functions, and I always define them by, you know, capital N, capital L, and then to the power 1 and of the real numbers, or capital 1, capital L to the power 2 of the real numbers, or things like that. We saw a couple of spaces of this type last time. The space I'll define now looks the same way, but it is not written with a capital L, it is written with a script L. So it is written like L, but then again we have a power, and then instead of writing the real numbers, we write the natural numbers. Now, what I did last week was just to introduce the space to tell you what is coming in this course. Now I will give an exact definition of this space, and we will deal with it in details. So the way this is defined is it should be a space consisting of sequences. So this is the collection of all sequences of this type that we are looking at here. And you know, from last week we actually had a shorter notation for this. So we also write it as xk, the collection of sequences xk, and then we write k going from 1 up to infinity. So we look at all sequences of this type that satisfies a special condition. And the condition is that if we look at the sum from k equal to 1 to infinity of the absolute value of xk, then we get a series that is convergent. That means whenever you try to calculate the sum of this series, you get something out that is finite. So that means what we are defining here is simply the space of sequences so this is the space of sequences xk, k going from 1 to infinity, for which, and now we can use a word that most of you heard at Mathematics 2. So what you see here, this is exactly the condition that your infinite series, the sum of xk, is absolutely convergent. So this is the space for which xk, k equal to 1 to infinity, is absolutely convergent. So if you go back and you look at your notes from the last lecture, you will see that the structure in this definition is exactly the same as what I used last week as we spoke about the capital spaces. So you see, again, there's a 1 here, and this 1 is reflected by that we have just the absolute value to the power 1, and that we here put in the n. This is because this is the index set for our sequences. So you see here we look at xk, k going from 1 up to infinity. So this is exactly the set we have here. So this explains the structure in the notation. So what we want to do is to relate this space to what we have discussed last time and also today. And it turns out that this space is actually a Banach space. So what is the number of the theorem? Is it 313 or what is it? So this is 321. So the theorem tells us that L1 of n is a Banach space. Now, actually, I have not completed the sentence yet. You see, the way it looks now is exactly like the way I formulated it here. Here, I just stopped the sentence. I said, CAB is a Banach space. But this is because on this space, we already knew how to put the norm. On this space, we did not put any norm yet. So before I complete this sentence, I need to tell you what should be the norm. So it is a Banach space, but respect to its norm. Now, if you go back and we look at the definition of the norm, then the definition should somehow inspire us to how we can define the norm on our space. And if you look at the condition that is not stated here, so not one of these properties, but if you look at what is stated up here, you actually will be able to guess what the norm should be. So what this condition says is that the norm should be something that to each element in the space associates a real number. How can we associate a real number to these sequences? Actually, if you look at the way the space is defined, you more or less have given this to you, because we are looking at exactly the sequences for which this is finite. That means this number is something that is associated to the sequence, and this is something that, by definition, is finite. So that means if you look at the way the space is defined, you will be able to, more or less, to guess what the norm should be. So it turns out to be correct. So it is a Banach space with respect to the norm. And now, again, we use this double bar for the norm. But again, because it is a norm that we are using many times, we will have a special name for the norm. And since this is the space that is called L1, we will actually denote the norm with the norm bar and then a little 1 below. And the way the norm is defined is exactly this expression that we know is finite. And the proof of this is something that you will do at the exercises today. So what you do is you look at the first condition, that is the one that is stated here, and you say this is satisfied because we have defined the norm such that this condition is satisfied. So what you have to do is to check that these three conditions are satisfied. Now, before we take the break, I would like just to generalize this a little bit. What we do is to replace this number that we put here, the number 1, which was reflected in this absolute value just being to the power 1. We will replace that by some number p. So we will consider exactly the same space. It will now be L and then with a p. And then still the natural numbers. And this will be defined as the set of all sequences xk, k from 1 to infinity, for which, and then we take xk to the power 2, to the power p, and we ask for this to be finite. And then the question is this a norm space? Is this a Banach space? So you say, when I ask the question, is this a norm space? This means you should think about how would you like to define a norm of that space. And there are some problems in the discussion of this. So I think I will not give you the solution now, but this is something you can think about in the break. And then when we come back, we will start to discuss this. How can we define a norm on this space? So let's take our break, and let's say we are back at 2 o'clock.